So welcome everybody to this Discover Us webinar. Okay, today we have Melanie Schranz from Lakeside Labs in Klagenfurt, Austria, and she will be presenting this webinar on unlocking nature secrets, engineering cyber physical systems with intelligence. And so Melanie holds a PhD in information technology, and her work has focused on developing decentralized algorithms for the coordination of autonomous cyber physical systems of any kind, inspired by natural swarm phenomena like observable in ant colonies and bear flocks. She has contributed extensively to this field through numerous publications in high-impact journals and conferences, and her research has been pivotal in advancing practical applications of swarm in areas such as swarm robotics, bottom-up optimization in production processes, or resource allocation in the edge for cloud computing. She is very active in collaborations with academy and industrial partners, leading innovative projects that bridge the gap between theoretical research and real work implementation. So thank you very much, Melanie, for accepting to deliver this webinar, and the floor is yours.
Okay, thank you very much, Rosa. Thanks for the kind introduction. So I'm very happy to be here and to speak to you. And I would like to first welcome you to, I would rather say, I try to structure the webinar as a kind of journey to see the strategies that evolved over millennia and are now used with cutting edge technology. So in my talk now, this Unlocking Nature Secrets, Engineering the Cyber Physical Systems with Swarm Intelligence, we will explore how the collective behaviors of different kinds of animals, including ants, bees, fish, flocks of birds, can inspire innovative solutions for these complex engineering challenges that we have. So this brings us now to the main core, where we will have a look on different kind of methods, but also on different kind of projects. But before I start with all the details on swarms, I'd like to use some words and lose some words where I'm coming from. So as you already heard, I'm from the Lakeside Labs. It's a non-profit, non-university research organization, and we are located in Klagenfurt, and we also live there, of course, in the south of Austria, close also to a lake. So maybe the name, the Lakeside Labs, somehow also emerges from it. And we are quite, focused research group with around 25 researchers, but are also very active in spin-offs, but on the other hand, also in scientific publications. So our goal is always to bridge the gap between university research and the industry. So I would say get ready to be a little bit more inspired by this incredible potential that we find in the intersection of nature and technology. So if we have now a look on this short video here, so nature has long been a source of inspiration for engineers and scientists in general, so seeking innovative solutions for complex problems. In cyber physical systems, we find ourselves exactly in this interaction or intersection of the digital and physical world, facing challenges that demand these kind of novel approaches that we will talk about today. So by emphasizing the power of the swarm behavior inspired by the natural efficiency that we can see in ants, the agility of fish, and the coordination of bees, we are creating a highly reactive and adaptive system that transforms complex tasks into a dynamic process where they are distributed and managed with remarkable efficiency and resilience. They optimize resource utilization and performance across our different kind of computing environments. So, but the big question is, what is the swarm intelligence? And for this one, I'd like to play here now another simulation that shows exactly what is going on. So we have a lot of different kind of agents, and each agent follows three very simple rules. It is that they check what is the agent doing beside me, so I'm getting a little bit closer if it's too far away. If it's too close, I go a little bit more away. And then I also check the alignment. And you can see here, we have here 600 different individual agents that form in a quite short amount of time a very nice swarm behavior. So there is nobody that is centrally dictating them where to go, where to move, but they freely form such nice flocking behaviors that we can observe in birds or fish. And what is also interesting, if you follow their behavior, they are never static. So they always try to adapt. They see what's happening in their neighborhood and try to find a way that is good for the entire group and also for themselves. So this brings us three main advantages that we have with these kind of swarm systems. So we have the adaptivity, where the individual agents can adapt to whatever comes and is then open in the environment. Then we have robustness, meaning that if there is a fail of an agent or it's just broken, could also happen now with this fish. It's also, I think, a nice illustration. It simply is not longer part of the swarm. The swarm mission can be still accomplished. And also scalability is something that we can achieve with all these kind of swarm intelligence, as we have local rules that are executed on each and every agent and can therefore have this scalability issue compared to any kind of central systems. So if we bring now all these things together, we now simply imagine being part of such a fascinating swarm. So a community where really every member counts. So this is the magic of swarm intelligence, I would say. So in this swarm, we are all equal, but yet unique. So we follow simple local rules, and each member communicates also with the neighbors. So this actually sounds quite simple, right? But from this, something extraordinary emerges. So without this central control that performs this dictation, we develop these amazing abilities like we've just seen in the simulation before. So a swarm is then able to quickly adapt, shows incredible robustness and scales effortlessly. So emergence is something that we use where the system functionality arises automatically from those interactions. And these natural principles inspire us to think differently. So in a complex world, the swarm shows us that true strength comes from simplicity and collaboration, and not from single players. So, therefore, a big motivation for, of course, swarms in cyber-physical systems. So the motivation for exploring swarm intelligence stems from this rapidly increasing interconnected any kind of systems, I would say. So we have here three very specific examples with Internet of Things, smart mobility, any kind of networked robots. And these systems become more intertwined and interdependent. So we face sometimes really unpredictable increase in the complexity, both in the development and in the operation. And by mimicking these decentralized approaches that we have with these self-organized principles that we can observe in biological swarms, we can develop more adaptive, resilient, and scalable systems capable of handling different kinds of challenges that are posed by our increasingly interconnected world. And so we reach a world where collaboration is at the end not just a buzzword, but a powerful force of nature where agents work together with the wisdom of a swarm. So in such a system, we don't rely on a single mastermind, is that we work with the collective intelligence of the many that we can find in these systems. So each cyber-physical system contributes to a greater whole. Like ants seeking the best food for the colony, our agents tirelessly search for the optimal solution. So they make decisions locally, although their impact is felt quite globally. And from all these kind of principles that we have seen now, we will come now to many applications where we already use now at Lakeside Labs this agent-based approach for the swarms, where we have the swarm intelligence really from the bottom up. So I tried to structure some selected projects in our group into different kind of application areas. So it's not all of the projects that you will see. And I also don't want to talk about the individual projects themselves, but so no general objectives, no consortium, but I really want to focus on how we bring this concept of swarm intelligence to swarms of cyber-physical systems of any kind of application. So I also try to add here and there some publications, as this presentation is going to be recorded if you want to see then something afterwards, so please have a look. But by far, I wasn't able to manage all, so please, if you're interested in a very deep dive into swarms in cyber-physical systems, visit my Google Scholar profile or the ones from my colleagues. So let's start, I think, with the different kind of ideas, and everything and all the ideas that we are following started in a specific application area, and this is our contribution in swarms in robotics. So a very first step was achieved with the CP Swarm project, where we worked on a tool chain to model, simulate, and optimize, and of course, finally deploy swarms of cyber-physical systems. So we had in total 3 different kind of use cases. So we were working on swarms of drones, autonomous trucks, and swarms in logistics. And this kind of building this kind of tool chain was very important for us, because it gives us a sense what is even possible when using swarms. So one of our application partners developed a set of flying drones that we used throughout this project. And we tried to bring in different kind of swarm behaviors. So as all of us know, especially in terms of robotics, we always need to care additionally about security, safety. So human in the loop things. So it's not possible to just let this swarm fly and do something self-organized. This is not working at the end for a final demo. So therefore, we come up with this solution that we say, okay, there are specific parts that need to be secured, but we can, in a secure environment, have a specific self-organized behavior where there is also a quite specific entry and exit point for the swarms of drones, like in this case. And so therefore, I just wanted to illustrate this principle in this state machine, where we, for example, use for the coverage mode a completely self-organized behavior. But as soon as a target is found, we step out it and do something different, do something deterministic. Let's put it this way. Then we could go again into a self-organized behavior like tracking and so on and so forth. So from this output, we were able to work on different kind of follow-up projects, and this is also something where we then went into the Backride project, where the goal was here to have an automated ship inspection. So we were using 3 different kind of robots, not like in the previous project, only how to say a more homogeneous swarm, but here we have 3 different kind of robots that interact. So we have the drones that are covering the ship hull from the top. Then we have underwater drones that do this, of course, from underwater. And then also these kind of magnetic crawlers that got then certain information and also organize themselves in a swarm to, again, perform the cleaning and the inspection on the ship hull itself. So there was the strong focus was, of course, also on the interplay of the robots. But as we come from the drones sector, we used a swarm of drones to search these defects on different kind of levels, so of different kind of instances from the ship hull. So we went closer if we detected a certain type of damage, or went more back. So this produced somehow a 2.5D space, as we call it. And this was then, at the end, quite a nice use case. If we also know the background, how costly such a ship inspection is at the end, and what kind of benefits we can reach here with an autonomous system. So from all these drones, we take a step further to defense applications. So I wanted to bring this here because I think this is quite on topic also nowadays, unfortunately. But still, we thought about, when we already have this kind of knowledge at our institute, we should also use it in a way where we would say how we can perform or work in terms of defense with different kind of drones. So the main idea is, maybe the next slide is a little bit better, that we have a set of drones that have the task to attack a certain target. So there are, of course, multiple principles around that would say, okay, let's, I don't know, shoot them down, or use different kind of nets or things like that. We went the other way, that we say, let's use drones that try to be part of the swarm, pretend to be swarm members, and mislead this behavior using different kind of behaviors that mimic being part of the entire swarm, but misleading the full swarm then to a different target. And this worked quite well in different using different kind of algorithms. So at the very beginning of our research, of course, you start with, we know, of course, the swarm intelligence algorithm for the attackers. So this is, of course, not the reality first. So we tried it with different kind of attacking algorithms in terms of a gray wolf optimizer, or also a slime mold algorithm. And then our idea was then to use different kind of additional rules for the defenders, so they infiltrate in the swarm and mislead it while they know this algorithm. But we went one step further, that we say we do not know these kind of attacking algorithms, and trained the different defender agents with machine learning components. So therefore, we specifically used the Unity game engine, different kind of reinforcement learning methods, so multiple approaches. And at the end, it worked out quite nice, I need to say. This can be seen here in the simulation results. So we will now not go over every detail, but please have a look on our publication, where you can see what is even possible. So it's interesting just to say that the number of defenders, there is no need that this one needs to be quite high. Already with 3 or 4 in relation to, I don't know, somewhere 10 or 11 drones, attacking drones, we can reach already a misleading of the entire swarm. And this was quite a nice success. And we really hope that we can further work on this one, as this could bring very interesting results also for other domains. Okay, so as I said, these are 3 selected projects. We work quite a lot on robotics at Lakeside Labs and swarms, but from all these ideas of local rules and local agents, we came to a completely different topic. And this is something where we thought, okay, why agent-based modeling and emergence is not taking place also, for example, in production plant optimization. And so specifically, we're talking about production plant optimization for flexible job shop scheduling, where we have and focus on a high product mix. So this is a quite interesting setting that we have, especially in the semiconductor industry. So we work together here with Infineon. What is really an interesting use case for us, that we say the bottom-up approach of defining different kind of agents. So where we have machines that can be agents, where we have lots that can be agents, where we have queues, where we have, of course, a multitude of machine types, single batch processing. So the complexity is somehow never ending. And we have here an agent-based model at the end that can not only optimize a subset of the plant like it's nowadays possible with any kind of linear optimization methods, but as we only consider local information, we can optimize the entire fab from the bottom up. So this works here with 1,500 products, with 300 processing steps, each of them, and a fab with, so the number is here missing on the slides, but it's around 2,000 different kind of machines that are used in this fab. So it's very interesting that so we just thought maybe let's give it a try and check what is really working. So at the end, we're still working actually on one of these projects, but what we were able to produce already is a swarm intelligence library of, as you see already, a quite huge amount of different kind of algorithms. This overview now excludes the variants. And what we found in doing all these kind of research and experiments is that exactly the algorithms that work on food foraging behavior, so on any kind of searching for food, work really the best. So bringing lots to hungry machines is really a very great combination. And this is also the way how we at the moment choose the different algorithms to bring them now in the next step to the digital twin of the fab and see how it works under more realistic settings, I would say. So for all these pre-selection, we constructed an abstract simulation framework with the main requirements and main constraints that we also face in the fab. But now going a step more, how to say, closer towards this fab, this brings us quite nice insights that we will see now in the next upcoming months what happens. But what happened so far, I'd like to just give you an input. So for all these production plant solutions and ideas on the algorithmic part, you can find a set of different papers. These are just two selected, but there are multiple more on all the algorithms. Is that we always used different kind of simulation setups. So from a small, medium to a large fab model with different kind of machine types, as you see, product types, and so on. And we always evaluated here the flow factor, the tardiness, and the utilization of the individual machines. And for example, here is a result of the Hohmann algorithm. Just exemplary is that we can also achieve here an increase of, for example, the uptime utilization of 4.4%, what is really nice. And we've seen now in different other algorithms where we already did the first step towards a digital twin that we are able to show similar results also then in the close to real fab, I would say. Okay, yes, so this is about the production site and swarms in production plants. Some projects that we already and still working on out of the idea of all these production plants. So it seems that we are also emerging at Lakeside Labs, so really coming from one application area to the other, because we simply also see that exactly this agent-based modeling and bottom-up approach is very beneficial. And it's also beneficial for swarms in edge cloud computing. So at the moment, we are working in 3 different European projects that work exactly in this domain. What is not true in total, because in the Mythos project, we also consider the fog, so the edge fog cloud continuum for ACES and glaciation, the edge cloud continuum. And we have here different kind of tasks that we want to achieve. For example, in ACES, we work on self-organized workload scheduler for the edge microdata centers. In glaciation, our task is to search data and perform different kind of data moving using a distributed knowledge graph. And in Myrtus, we also have a quite, how to say, a similar task than in ACES, but it is on the edge of fog continuum and perform here the resource allocation. And I'd like to jump into some details of the tasks that we have in these kind of projects. For example, in ACES, we consider an edge continuum that is built up with interconnected cluster heads, each managing a pool of resources of CPUs, storage, GPU, whatever kind of resources available. And that actually present our resource agents. So then we have the incoming microservices. And as we, in all the projects, already work quite close to Kubernetes, we also call them pods that have some kind of specific resource and efficiency demand. And so these represent in our demand agents. So this agent-based modeling brings some challenges that we need to consider here. So, for example, we need to, what we are doing here is we consider the hardware as a pool of resources instead of the resources on node level. So this is maybe a main difference here. Then we, of course, include two different kind of application types that need to be processed by the continuum. For example, long-running applications, batch or stream processing. And what we also do here is we work on the relationships among the different, among the pods, like any kind of interpod relationships, parallel processing, and dependencies. So, for further details, also please consult the paper that is here at the bottom of this slide. So we will not go over everything, but what I want to tell you is that in the system, the pods and the resources aren't just passive entities. So maybe this is the most important thing here as well. So they are also active agents like we had it in the other applications. So they act, they interact, they make decisions autonomously. And this dynamic interplay leads to something quite remarkable. So scheduling emerges also here from the bottom up, and this in real time. So there is no central controller dictating every move, so where each pod needs or should get processed. Instead, the system self-organizes, and the result is a scheduler that is inherently adaptable, robust, and scalable. So it is able to flex with changing demands, disruptions, and it can grow seamlessly. So what we've created with this kind of scheduler is a little bit more than a scheduler. So it's an autopoietic resource allocation system at the end. And like a living organism, it continuously recreates and maintains itself, adapting to this environment where we are currently in. So, so this is also reflected in our simulation results, where we can improve the resource utilization and the satisfaction rate by exploiting the slack resources using this bottom-up approach. Specifically, we are using here the artificial bee colony algorithm and the hormone algorithm, and we compare at the moment it against a random algorithm and something that we call the best algorithm that is computationally extremely intense and and far away from any efficiency, I would say. So what we found with the bees is now a solution that shows great utilization and improved satisfaction rate combined with a flexible local algorithm that is at the end not computationally intense, what is also very important for these fast reaction. So yes, this is in this paper, there is also these there are even more details on the algorithmic part, how to perform those agent-based modeling, and how we then come up with this kind of design methodology. So this brings us to our next idea with the Myrtus that is not that far away, I would say, to the previous project. The only thing that I'd like to highlight here and point out here is that we now talk about Edge Fog Cloud, and especially about offloading of the different kind of tasks that can have their entry point at the edge at the user. So we again try to stick with our modeling approach, where we say we have the resource agents on the one hand and the edge agents on the other hand. And the edge agents, the demand agents, sorry. And so again, with a specific demand for a certain processing and storage that needs to be found a way. So the main idea is really to find a good way that we say we have enough resources on an agent so that this algorithm can be processed. In our current publication, so these results that you can see here at the moment are not published yet, so we are currently in submitting the paper, but we want to compare it again with a kind of random algorithm. So the pods select the next agent randomly from the neighbors. Then we have a greedy algorithm where the pods select the next neighbor with simply the maximum pheromone value. And as last, we want to introduce an ant colony optimization algorithm. So the ACO is probably known to the one or other, typically used in routing problems. And we found actually that this kind of constellation that we have here with Edge Fog Cloud is quite close to any kind of routing. So let's give it a try and see what is the outcome. So the pods select the agents from the neighbors with a specific probability related to the pheromone value that expresses the utilization and the communication cost. And at the end, we have here different kind of simulation results, and where we at the moment have the focus here for this project is that we evaluate the dependency of the fog and cloud. So because we of course have this kind of strategy for Edge Fog Cloud, because we want to bring all the data as good as possible back to the edge. And with these kind of algorithms, we want to allocate our resources as good as possible at the edge. So therefore, a measure that tells us how good is our dependency to the fog and to the cloud is something that is very important to us in our evaluations. Okay. Good. And last but not least, I also like to lose some words for the glaciation project, where I'm really proud of the publication that you can see here on the slide is at the moment presented at Jan's conference. I don't know at the moment, I think it was today in the afternoon, but still these days at Jan's conference in Constance in Germany. And so what we did here is that we have here a distributed knowledge graph where all the data is distributed. So first of all, it was quite hard to get from a centralized knowledge graph to a distributed one. But at the end, the main idea is to get some kind of additional scalability, energy, and bandwidth efficiency. The dependability and trustworthiness are very big issues here. And the distributed knowledge graph also needs to act adaptive in terms of data movement and search, again, on a minimal expense. So if there is a query coming in from any kind of node, so we try to always focus on the edge. We also use here the concept of ants to, first of all, use a set of forward ants that search for different kind of data snippets, I'd like to call them now to be more understandable, and bring them then together. And so what we are doing at the moment is that we use the ant algorithm for data search. So this produces us pheromone concentrations on the different connections between the individual nodes. that of course evaporate over time. So evaporation is also something that we try to evaluate a lot, because this gives us different kind of ideas in terms also of the hit rate, like we see it here on this slide. And as soon as we see that there is a strong need maybe for a specific type of nodes for a certain data that is maybe located somewhere else, we perform here now a data movement strategy that is based on this pheromone values. And with this data movement, we can then increase the data search. The data search is getting more efficient, so we have here then an increase of the hit rate. And this is something that now, of course, now also concludes our edge fog cloud methods that we want to use for swarm intelligence, and brings us to what else is capable. So we are always searching for new kind of topics, because we find it quite nicely to see how complex problems can be solved using this kind of self-organized strategy by this agent-based principle. And this brings us to our last topic. It's the swarms to enable privacy. So something brand new from our side, because also the application area, you can see it now here, is something that we've never really touched before. It's a completely, so some of you would say, okay, it's a completely logistics environment. So we have a set of freighters that get a set of orders, that also have a set of, for example, trucks to deliver these orders. But what happens if a freighter runs out of resources? So runs out of available trucks, has too many orders. He also always wants to be best friends, I would say, with the customers. And so, but also not telling the other freighters that I'm low in resources. So therefore, there is always someone at the moment in between, sitting in between. We love to call this a broker, that is taking all the different kind of information. It's the trustworthiness should be, of course, given for the broker, and we need to trust him or her. And so our idea was, why not checking for something different? Because when we talk about swarms, we have the possibility that not all the information needs to be shared with everybody else. So let's think about just eliminating this broker in the middle and thinking about the distributed system. And this is a thing that we are currently working on, where we first need to check what needs to be done and needs to be known from the swarm algorithm to enable the privacy for these kind of providers. So what we try to do and how we try to bring up the system model is that we say, okay, the freighters are known to the orders, for example. The orders know only then a reduced set of the other orders. The trucks do not know each other. So certain constraints, as you can see. So to really reduce this amount of what belongs to whom at the end. And we tried to bring here in also our swarm intelligence concept. So I will not go with you now over every block, but just giving you an idea of what is going on at Lakeside Labs is that we, of course, we have now this pool of orders. We have the pool of trucks that where, of course, behind somehow each truck, there is a specific freighter. And the idea would be then that we use a specific artificial bee colony algorithm where we perform a truck selection phase of the orders themselves. So there are also some constraints and some requirements that we need to assume for such a new application idea, like the orders can somehow decide by themselves. So at the moment, it's maybe a little bit still a step far away from the real application, but we will approach this. I know it. At the end, we also need to show that if we have a certain number of trucks and a certain number of orders coming in, that the performance of the algorithm is still okay. So we always evaluate the number of empty runs, what is very important also in terms of CO2 emissions and energy costs in general. And we were quite happy to show this in our newest publication. I just talked with my colleague Maria before, and it's now just got online today. So yeah, and I would say have a look on that. I would be very interested whether there is also some feedback from people around how things like privacy could be solved using swarm intelligence and not sharing each and every information from all the participating entities, as this would be necessary if we would have a central system that manages all the incoming orders in this case. So thank you very much for taking the time. Be swarmy, and looking forward to your questions.
Thank you very much, Melanie, for this very comprehensive presentation. So please, all attendees, you can write your questions in the question and answer tab. I will start with one question from Xavier Casas. So he says, you mentioned self-organizing algorithms and also reinforcement learning. I was wondering if you have found ways to work in the intersection between them. Can a self-organizing swarm algorithm be expressed as a reinforcement learning problem?
Okay, yes, it's a very interesting question, and we made already our first, I would say, baby steps towards it. So what I can only recommend is to start in the self-organization way with all these kind of learning approaches, is especially when you go towards specific individual agents, is to use, for example, the Unity ML agent. This is a quite nice environment where you can learn rules using, for example, robotic systems. And this is a really nice combination. So we are still not at the end. So I have no clear answer yet. So we're still also making our steps towards it. And this is also something where we would be very happy to see in future whether generating local rules using some kind of machine learning tool would be maybe even a step more flexible. So for certain swarm, including it into certain swarm behaviors. So if we talk about local rules, there's a specific set that we have there. And if we would replace the one or other with machine learned components that can still adapt over time, this would be a very interesting outcome.
Thank you, Melanie. So there's another one from Juan Cadavid. So he says, great presentation. What would you say are the limitations of the swarm intelligence approach? When not to use it?
Okay, you should never use it if you have, I would say, a good number of agents. So swarm intelligence always shows its benefits if you have very complex environments with a multitude of different kind of interacting tasks, I would say, and interacting information. So if you have a system that I don't know, if we come back to the robotics domain, because it's for me easier to explain, if you say you have 3 robots that needs to cover a certain area that is already given and that has no uncertainties at all, please go for a multi-agent system and do it that way. You should use a swarm system as soon as it's getting complicated. And as soon, I would also say, it's somehow harmful for humans.
Thank you. Okay, so there's another one from Eduardo Irola de Acevedo. So could you please explain which algorithm does the SAR behavior CPS swarm used? it is by Inspire as well, or did your group create it?
Sorry, I didn't get the first part of the question.
If I understand that it's asking about the which algorithm is used in the SAR behavior CPS
Search and
swarm.
rescue behavior, yes. Okay, so in the search and rescue behavior, we use the combination of different kinds of behaviors. I would say it's not only swarm behaviors, but also very deterministic ones. This was our first step approaching bringing swarm intelligence to the autonomous part. And for the first part, so the search and rescue behavior was in the CP Swarm project was designed in a way that we had a set of swarms of drones that were covering an unknown area. So therefore, it was important that they were able to, so we use different kind of approaches. For example, one is what you also use in other drone things is formation flight. This is something where you come over where you approach the swarm intelligence advantages in this case. As soon as a target is then found, the drone would hover over the target in our scenario. Maybe it's not the best if it's about humans, but in our scenario, it was a mobile robot. So we performed the hovering and wanted also to track. So if this target would move to another place, this drone would simply somehow perform a following activity. And this is something where we have not implemented swarm algorithms. So we love swarm algorithms, but we also see where it is beneficial and where not.
Thank you. Okay, if there are other questions from the audience, please type it on question and answers. I have at least a couple more. I have a question with regard to the Swarm Intelligence Library that you presented in your slides. So how it works? I mean, is something that is available for the community and people can use it in other swarm applications, I'll say, or environments?
So I think you're talking about the swarm library that I presented for the production plant scenario.
Yeah, I think so.
Yes, so we have all the algorithms together with the simulation framework online available. It is also part of the papers. So in every paper or in every newer paper, let's put it this way, because at the very beginning we just built it. But in every new paper, you find a reference where you to this Swarm Fab Sim. It's called a simulation framework that was for this abstract simulation part created in NetLogo. But it is an agent-based simulation environment. At the moment, for all the new applications arriving, we use the Mesa library in Python. But at this time, this was the most appropriate environment. So we started to build it up. And yeah, there is a set of different kind of algorithms available there. And you can, of course, use it, but it is very application specific. I think it's still very valuable because you can get an idea of what is going on agent level. And this is quite nice to have a look at.
So this explanation links nicely with my other question, because I would like to know if in the projects you have been describing, if you have been basically simulating and modeling the behavior, or you really have implementations of the agents that can be deployed in the devices.
Okay. So typically when we start with a new application domain, like we did it in the production plants, but also like we do it at the moment for the Edge Fog Cloud, we always use somehow the same principle. So we first go towards an abstract simulation environment. At the moment, we really love to use, as I said already, the Mesa environment, the Mesa library, using a Python implementation. We try to get all the requirements as good as possible and bring them into the framework. And we simply test first algorithms. So, swarm intelligence is all about observation. So we need to have an environment where we can simply change different kinds of configuration and test the effect on that. And as soon as we would say, okay, we now found specific candidates that work quite nicely on the problem and fulfill the needs that and the requirements on the objectives that we have from our application domain, we transfer them to and integrate them to the real systems. So this is something that at the moment at Lakeside Labs happens all the time in the robotics domain. For the production plants, we at the moment already do the transfer to the digital twin. And for example, for the Edge Fog Cloud domain, we have already one project where we also started this integration already. So first we do all the testing and evaluation in the abstract, so we cannot hurt nobody's system. And then it goes towards integration as soon as we find suitable candidates with suitable configuration settings.
But then these solutions are application specific, or you have any Asian library that you typically will use?
So we have some kind of, how I would say, for the agent-based modeling part, we typically have a quite nice approach already developed internally to perform this modeling. But for the algorithmic part, they are very application specific, as we want to be very close to the application. Each application comes with a very specific set of key performance indicators, and this is something that we work on.
Yeah, but I was referring to the actual integration. When you implement I understand that you implement somehow the agent integrated with the devices, no? Or when you say that you integrate, what do you actually mean?
Talk about integration is that we then so we always model the system as an agent-based system. So this means, for example, in the production plant, it's the most easiest for me to explain, is that we have, for example, a set of different kind of machines. Each machine, for example, presenting a specific agent with specific constraints, specific limitations. And if we go towards integration, we have an agent. Yeah, it is a software agent actually that runs on this machine and of course needs to have access to the local information on the current processing status, what kind of product is currently processed, what kind of status the queue has at the moment, things like that. And this one is then also deciding, for example, which lot of which product to take next, and what is most beneficial for the current process.
Okay, thank you. Thank you very much, Melanie. And with this, I would like to close the session. Maria, I don't know if you wanted to add anything else.
No, everything has been said. Thank again, Melanie, and also all the attendees of the webinar. We look forward meeting you again in the next webinar or one of the following ones.